Let's now look at weight initialization. At first sight, it looks like initializing all our weights to 0 may be just fine. But it turns out that weights initialized to a fixed value like 0 will cause the neural network to hardly converge. And that's why many times we use random initialization, where the weights are drawn from a normal distribution with mean mu and standard deviation sigma, and where the normal distribution obeys this formula right here. Although using random initialization of the weights is already better than fixing the weights initially, we could enforce some constraints to make this random initialization more efficient. The first is that the weights are drawn from a normal distribution with mean equals 0, and also that the variance sigma square is the same throughout the whole network. So this means that if we pick this hidden layer here, because we have this hidden layer, this other hidden layer, the output and then the input. So if we pick this hidden layer right here, we could compute the variance of the values in the neurons we have in this hidden layer. And here we have that variance to be equals the sum of weights multiplied by values in the previous hidden layer. So let's take, for example, let's say this L is this hidden layer right here, which is, so let's say L equals 2. If we have L equals 2, what we're saying is that for each and every neuron here, like if we pick out this neuron, obviously the value we get here is by multiplying the weights, that's this weight, by this value, plus this weight by this value, plus the weight by this value. And that's basically what we're doing here. So we have the sum of the weights by the values in the previous layer. And since here we've picked the layer L, the previous layer is L minus 1. And if L equals 2, the previous layer is 1, since 2 minus 1 is 1. And so we fall in this layer right here, or in this hidden layer to be more precise. Also note that the summation is done from I equals 1 right up to the number of neurons in the previous layer on the L minus 1th layer, which is NL minus 1. If we were in this, we would have NL. Throughout the section, we shall suppose that the weights and then the inputs are independent and identically distributed. We also note from our knowledge on probability distributions that the variance of a random variable x is the expectance of the random variable square minus the expectance of the random variable all of that square. So we have ex square minus ex all that square. If these concepts are new to you, you could check out our course on probability distributions. Then we also know that the variance of x plus y, that's two random variables x and y, the variance of x plus y is the same as the variance of x plus the variance of y. And clearly from here we have the variance of a sum. So because this tells us that if we have, say, x plus y plus z will be the same as var x plus var y plus var z. So the variance of a sum is the sum of the variance. And we could apply that here. We have the variance of the sum, which is equals the sum of the variance. Now to simplify this expression we have here, we are going to make use of the fact that the variance of x times y, that's two random variables x and y. In this case, this is our x, the weight, and then this is our y, the values in the neurons. So here we have var xy is the same as the expectance of x squared var y plus the variance of x times the expectance of y squared plus the variance of x times the variance of x. And also thanks to the fact that we draw our weights from a normal distribution of mean 0, it simply means the expectance that we shall get from here will return to 0. So here we have, like we had this here, like we're coming from this, which is equals the sum, and then we've extracted just this part here. So if we take this part and put this, what we'll put right here. So we have the variance of the weight by the previous neurons is equals the expectance of the weight square. We're just applying this formula. We're considering that this is x and that this is y. So we have the expectance of x square, the expectance of the weight square, times the variance of y, times the variance of this output here, or the input neurons that's in this layer. So this expectance, or rather the variance, plus the variance of x, that's the variance of the weights, which is this, times the expectance of the neuron square, that's it here, plus the variance of x times the variance of y. So that's what we had here. And as we have said previously, the expectance is equals 0. So this turns to 0 and this turns to 0. So that's it. We're left with the variance of the weights times the variance of the output or the input neuron. By input here, we're referring to this. We're supposing that this is like our input and then it's our output, although they are hidden layers. So we'll see how this expression right here helps us to leave from the variance of the weight by the neurons equals the variance of the weight times the variance of the neurons. Then let's get back to the proof to understand what went on. Here we had variance of xy equals expectance of xy square minus expectance of xy, all of that square. What we did here was apply this formula which we had presented previously. If you replace x by xy, you should have this. So x here becomes xy, and then x here becomes xy. Now xy square is the same as x square y square, so we have expectance of x square y square minus the expectance of x times expectance of y, all of that square. The reason why we're able to write this is because since these two are independent, we have that the expectance of xy is the same as expectance of x times the expectance of y. This is when the two variables x and y are independent, and that's based on the assumption we made earlier. So since we have that, we leave from expectance of xy equals expectance of x times expectance of y, and all of this square. Then expectance of x square y square is the same as expectance of x square times the expectance of y square, since these two are independent. And then we have this turn into expectance of x all square times expectance of y square, since this is like ab square, so it becomes a square b square. And that's what we have here. Now expectance of x square, expectance of y square is maintained, and this here is transformed. Now if you come back to this formula right here, you'd see that the expectance of x square, if you make this the subject of the formula in this equation, you would have that the expectance of x square is the same as the expectance of x square minus the variance of x. So if you take this to the left side and the variance to this right side, you will have expectance of x square minus variance of x, and that's why we have now this relationship right here, where we replace expectance of x all squared with expectance of x squared minus variance of x. It's coming from this. And similarly, we have expectance of y squared minus variance of y. Now if we have to multiply this, we would have this remains intact. Ex squared times ey squared turns to ex squared times ey squared. Ex squared times vy, we have it here, vx times ey squared, vx times vy, sign changes. Then we have the negative that we have minus all this. So simplifying again, you have ex squared, like this is the same as this, so just cancel out. Now we have ex squared vy, which is this, minus vx ey squared minus vx vy. And if we rewrite this ex squared here using this expression, we have ex squared is the same as the variance of x plus ex all of that square. And so here we have vx plus ex squared times vy, which is this. And then we have vx, this, times ey squared. Similar to what we had here, we have vy plus ey, all of that square. Then we have minus vx times vy. So now we have, if we multiply this term with add with this, we have this expression. This two cancel out, and we're left with this final expression, which is what we use right here. Now you may have noticed that there's been a slight change. Like now we have, instead ex all square instead of ex squared previously, there was a slight error which was made on the expectancies here, as we had previously ex squared, and that was an error. It's meant to be ex all that squared. Nonetheless, that doesn't change our result here because the expectancies actually are zeros, and it even makes more sense now since it's the expectance of the weights that's 0 and not the expectance of the weight square. So now as well we have this variance the same as the variance of the weights times the variance of the hidden layer output. If we get back to this formula we had initially, that is, we had this variance and it gave us the sum of this variance. Now after computing this variance, we have it as this. So if we replace this now with this product, we would have the variance of the weights times the hidden layer output being equals the variance of the weights times the variance of the hidden layer output, which is what we have proven right here. Also notice how we've taken off the indices I and K. Yeah, this IK is taken off. Yeah, this I is also taken off. This is because now that we're calculating this variance as a separate entity, unlike here where we're calculating the variance of the weights times this hidden layer outputs, now we have them as two separate entities, and the variance of the different weights, or the variance of all the weights, is considered to be the same. So we consider that to be needless specifying the input neuron or the output neuron, because the IK here, the I is for the input, like say this, and then the K is for the output. So if we have this weight living from year to year, we'll have the weight will be W11, but then the variance of W11 is the same as the variance of W12, W13, W14, W21, W22, WIK in general. So it's needless specifying the variance of WIK since they are all the same. So we just have them as the variance of W, since the variance of WIK for all I and K is the same as it's the same value. So we just have variance of W, and then it's the same for the output, or it's the same as for the values we have in this hidden layer right here. So that's why the variance of AXI is the same as the variance of AX. Now that said, we see that we could take this 2 off out of the summation sign here, because now they're like constant since they don't depend on I. So yeah, if we take this VW and VAX out, we have left with the sum of 1 from I equals 1 to NL minus 1. Obviously the sum from, if we sum 1 n times, is equals n. So here we have NL minus 1 times this. And so we could write that the variance of this hidden layer outputs is the same as NL minus 1, that's the number of neurons we have in this previous layer, times the variance of the weights times the variance of the hidden layer outputs in this previous hidden layer right here. And since we want the variance of this hidden layer to be the same as the variance of this hidden layer, and obviously throughout the whole network, as we said initially, this must be equals this. And in that case, this 2 we cancel out. If we make the variance of W the subject of the formula, we have that the variance of the weights should be equals 1 over NL minus 1. And this is the Xavier initialization technique, where we draw our weights from a normal distribution while making sure the mean is 0 and that the variance is 1 divided by NL minus 1. Meaning that if we are, say in this, we are trying to get the variance of the weights in this block right here, we'll simply use this formula 1 divided by the number of neurons here. So in this case, it's going to be 1 divided by 3. Other initialization schemes like the Glorode, which are similar to the Xavier initialization, ensure or draw your weights from a normal distribution with mean 0. But with the Glorode, for example, the variance is such that we have 2 divided by the number of neurons in the previous layer plus the number of neurons in the next layer. So in this case, we would have 2 divided by 3 plus 5.